All right, everybody. This is a video for the Conservation of Energy Lab. For this lab, you're going to use this website, which is this one here. Make sure that you follow the instructions. Basically, you want to have gravity at 9.8. You want to use the lab option. So when you click on the software here, you're going to go to lab. That will open this window. The ruler comes from here, and that will give you the natural length of the spring. Here is about 48, 49 centimeters. You need that to calculate the elongation. The elongation is calculated by subtracting whatever the displacement is on the spring due to different masses. So for example, for a 50-gram mass, you can place this on the spring. And if that happens, you want to stop it, okay? So there, right? You see that? Here the reading is about 56 centimeters. So 56, 55. So 56 or 55. You subtract that value with 48. And that will give you the elongation that you need to write in the table. The ruler reading, you can add it. Right, so the ruler reading will be 56 or 55. And then you should have the natural length as a constant that you're going to be using. All right, it's given here as well, but you should read it using the ruler. Now, mass and force. So if the mass is of 50 grams, the force is 50 divided by 1,000. That's the mass in kilograms multiplied by 9.8. So 0.49 will go here. For 0.05 kilograms is 0.49 newtons. Ruler reading, elongation, as I explained already. You can keep adding masses. Here in the lab, it says that you want to repeat this step by adding to 100, 150. So you can plot. You can do a plot of force divided by of force versus elongation. So you already have this reading, you remove it, and then you go to 100. To do 100, you just go here, or yeah, and you will change it to 100. And then again, now the reading is of 63, right? So it was natural length. Oh, let me go with this. Natural length was of 48. The elongation for 100 grams is 63, right? 63 centimeters. So 0.63 centimeters. So 63 minus 48, that will give you the elongation for 100. Same procedure. You place the mass value here, the force. So the graph will be a linear graph. If you plot all the masses as a function of elongation, it will give you a linear graph. And you can find the constant of the spring by doing that. The force divided by elongation, force on the y-axis, elongation in the x-axis. The slope of that graph, which is a line, will give you the k value. And you need that to find the energy, right? Using the equation 1/2 kx squared. All right, so if you go to Excel, you are going to create a spreadsheet where you have elongation in the x-axis and force in the y-axis. So if you have the elongation, let's do a couple of values, all right, that should be clear by that. So 100 grams, that give you 63 minus 48, that's 15, right? 15 centimeters is 0.15, and 100 grams is 0.98 newtons. And then we had 50 before. So let's go back to that. That gave us 55, right? And you are 55. So 55 minus 48, that's 7. So 0.07, I go 0.49. So I know 2 points is not enough, but still do this, at least to show you how to do this. There. So with a few more points in here, you can find the equation of the line as you did in previous labs. And that will be the slope of that line will be the K constant. And then using each elongation, you can find the energy. For example, let's just find the slope between these 2 points. Like, okay, 1.97. So if I want to find a potential energy, you can do 1/2 times K, can run it like that, multiplied by the elongation square. So that's the energy use. You can also find it by doing the area, as it says in the lab, right? If you do the area under the curve here, you can always, in this type of graph, you can extend the line, right? You don't have to do that. Extend the line here. Then you can calculate the area base times height divided by 2, and it will be the same if you think about it. All right. Because this will be the force, which is 0.49 times that. So let's see. If I do it using the area for the first point, will be base times height divided by 2. Wait a second. Force is in the y-axis. Why am I having this graph like that? Elongation and force. There's something wrong. The x-axis is fine. The y-axis seems off. Why? Let's see. This point, did I put it right? This data values, data labels, 0.15. This is 0.49. Should be here, right? Let's see what is this graph. Might happen. Maybe something wrong here. That's x and y axis. Since y-axis is doing this, is it interesting? Since when Excel is doing this? I thought it was always doing it. Is it doing that now? Insert, plotting values like that. It should be my x-axis, my y-axis. It should be plotting it properly. That's why it wasn't giving me the right value. So the value of the slope that we got wasn't right. Maybe need one more. Let's do another value. Might be that. So the lab is asking you to do 150 grams, I believe. Yeah, so let's do another value. These are the things that you guys have to learn as well when you do these labs, is identify that there might be a mistake. In this case, Excel is giving the wrong plot. 70 centimeters minus 48 is 22. So now we can do 0.22. And this is 150. So 1,000 plus 28, 1.47. Now let's do this like that. I'm not having the way we did the graph. Okay, yeah, so it seems like when you do 2 points, Excel messes up the graph. So then the equation of the line will work now. Okay, so that's the K constant, 6.5. 6.52 newtons per meter. So this is wrong. This would be 1/2 K 0.07 squared. And that was what we got before, right? With the area would be base times height. Base times height divided by about the same. So now we're getting something. The reason you're not going to get exactly the same values is because the trend line is giving you the slope. And remember that it might not be, you see, like there might not be 100% linear fitting. And it's only 3 points. So you will get more accurate as you have more data points. All right. So that's what you have to do. That's the only thing you have to do. Is a very simple lab. You will summarize your values in table 2 as it says here. And the idea is to find the potential energy and find the energy gain as you stretch a spring. The more you stretch, the more potential energy you will get. And then, yeah, you have to answer, does the work found as the area under the graph equal the loss in potential energy of the falling mass? Basically, you want to find the area, compare the area values with the formula 1/2 kx squared. All right. Remember that as the mass is dropped, right, the potential energy is converted into something, right? So the mass is moving. That's how you will answer those questions. So it's just that you can show a couple of graphs or one graph if you want, your table of values and your calculations. Okay? That is all for this lab.